Welcome back to the second part of Lecture 16. In the first part of this lecture, we examined droplet deformation, and we saw that in shear field, droplets can rotate and elongate and become ellipsoids. In this part of Lecture 16, we're going to have a look at droplet breakup. We're going to see that extensional flows are a lot better at breaking up droplets than shear flows, and the concept of when droplets break up and when they don't break up is very important in the design of devices such as homogenizers. Homogenizers reduce droplet size distributions, and so, for example, in the milk industry, smaller droplets are preferred because in the supply chain to get milk to the supermarket or to your doorstep, smaller droplets don't cream out so easily, and so you don't end up with a layer of cream on top of your milk. So, when we examine droplet breakup, we're going to introduce a graphical aid to help you decide whether or not droplets break up. We will also see that droplet breakup is very strongly dependent on the initial shape of a droplet. So, here on the board in front of you is a diagram called the Grace diagram. Now, the Grace diagram plots a critical capillary number, the critical capillary number for a droplet to break, as a function of viscosity ratio. The Grace diagram pertains exclusively to spherical drops. So let's start with spherical drops and see how we might break a spherical drop up. What sort of deformation field, what capillary number do we have to impose on a spherical drop to get it to become more than one droplet? So the result I've plotted on the Grace diagram here is for shear flow. The blue shaded region is that region where droplets break up. Outside of that blue region, droplets remain unaffected. Interestingly, there are bounds to shear flow. So the bounds where shear flow will break up a droplet is between viscosity ratios of 5 times 10 to the minus 3 up to 3.4 and above capillary numbers of 0.5. So we have a window of opportunity here for shear flows to break up spherical droplets. Now, interestingly, extensional flows are far more effective at breaking up droplets. Extensional flows don't have these viscosity ratio limitations, these bounds in kappa, and also the capillary number required to break up droplets in extensional flow are generally lower. So, the first key take-home message here is that extensional flows are very good for breaking up droplets. Now, underneath these critical capillary number curves, in the region at lower capillary number below either the white chain dashed line or the blue dotted line, you end up with droplets of a diameter which is governed by that critical capillary number. So if we take, for example, a viscosity ratio kappa of 1, we see the critical capillary number is 0.5. We recognise that the capillary number is written as R eta gamma dot over sigma. So for a particular gamma dot, given by a deformation field, for a particular system that sets the interfacial tension, and for a certain continuous phase viscosity, we can calculate what the critical diameter of the droplet would be that would remain unbroken, that would fall below a capillary number of, in this case, 0.5. And so we can think of that logic to say that if a droplet does break up, we can work out the size of the droplets that are formed, that no longer break up, the stable droplet size. So, extensional flows are good for breaking up droplets. Now, the Grace diagram pertains to spherical droplets. What if your droplet isn't spherical? Let's look pictorially at two scenarios. I'm going to start with spherical droplets. So if I expose a spherical droplet to a capillary number less than the critical capillary number required for droplets to break up, I will see the droplet elongate, and then if I stop the deformation, I will see under rest the droplet return to its original spherical shape. And that would be expected because we know that a shear or extensional field will elongate a droplet. But if the capillary number falls below the critical capillary number for droplet breakup, all we will get is a deformation. We won't enter breakup. However, if we impose the same deformation, the same critical capillary number, to an initially slightly ellipsoidal droplet, what we may see is that droplet deform and pinch and then break. So the key message here is that when we look at the Grace diagram, we will see critical capillary numbers below which spherical droplets won't break, but that is not to say that initially ellipsoidal droplets won't break. Now, we can plot these results out on a graph. So this is for extensional flow only, and again I'm plotting critical capillary number as a function of viscosity ratio, kappa. Let's start off by looking at spherical droplets, and we see the trend that we would expect from the Grace diagram. Now, if I look at 5:1 aspect ratio ellipsoids, I can see that at high kappa, high viscosity ratio, droplets will break up at significantly lower capillary number, orders of magnitude lower than spherical droplets. If we look at even more elongated ellipsoids, say a 20:1 ellipsoid aspect ratio, we'll see that these elongated ellipsoids break up very, very easily indeed. So, elongated ellipsoids are far easier to break up in extensional flow than spheres. And again, this is information that we can use if we're designing a device to break up droplets. Elongate them, then break them. Now, let's return to our Grace diagram for spherical droplets. We plotted capillary number as a function of viscosity ratio, and when we're thinking of the capillary number, we're thinking of the interplay of viscous forces and surface forces. And we've talked about shear flows and about extensional flows, and really what we've been talking about is how we change the viscous stress, how we change gamma dot, and what effect that has on our sphere. Now, don't forget, we can also manipulate the capillary number a different way. We can manipulate the surface tension of a system by adding surfactants. If we were to add surfactants, then of course we change the capillary number. And so an ultimate design of an homogenization system may involve extensional flows and, if possible, for the use that the homogenizer is being put to, the addition of surfactants to lower the interfacial tension to make the droplets easier to break still. Let's recap a few key points. We've been talking about droplet breakup. Droplets break above a critical capillary number, and we plotted for spherical droplets these critical capillary numbers on a Grace diagram. We saw that in shear flow there's a limited region for breakup. We saw, however, that extensional flow, we don't have that limited region, and so homogenization should involve extensional flows because they're far more effective at breaking up droplets. We also saw that the initial droplet shape is really very, very important. It's far harder to break up spherical droplets than it is ellipsoidal droplets, and the more elongated that ellipsoidal droplet is, the easier it is to break up. We must also remember that we can also use surfactants to help promote droplet breakup.